Okay, so let's kind of review what we have here. We have a toroid. This is like a top view. We're looking down on this donut-shaped object. A side view kind of looks like this. And yeah, it has 500 loops of wire. So we have one wire that just wraps around. There's 500 loops of wire in this toroid, and we're given the dimensions of it. So the toroid has a height. So if this is a top view, it's like coming out of the board, 2 centimeters. It has an inner radius of 4 centimeters, and this dimension is 3. So the outer radius is 7 centimeters. Now we place a current given by I max sine omega t, where again, let's just look at sine by itself. If we plot sine omega t or whatever, now the max, it oscillates between 1 and -1. And so the maximum current would just be whatever we put in front of that. There will be some time when sine omega t is 1, and that's the highest the current's ever going to get. So we call that I max. So the current in this loop, this coil, where I max is 50 amps. So it's a rather large current. And the frequency is 50 hertz. So, or 60 hertz. It's actually fairly typical, which we'll talk about later. Now, what is omega? Well, omega is the angular frequency, which is 2 pi times the frequency. So we have a problem set up. Oh yeah, and then this is a coil running out of room here. So now we place a coil that contains 20 turns. So it's wrapped around one section of the toroid, and we want to determine the EMF induced as in this coil. So, yeah, we want to find the EMF in this coil that we place around the toroid. Okay, so it seems like we might have a lot to do here. Remember, we're going to create a magnetic field inside the toroid. And you don't remember what that is. I don't, so let's figure that out. We'll use Ampere's law first to find what the magnetic field looks like inside the toroid. Well, let's draw it. Magnetic field line circles around the toroid. Let's say it looks like this. So again, this is that cross-section view of the toroid. So we have the magnetic field lines are forming loops. And so like over here, that's going into the board, it wraps around, comes out of the board. So these are the magnetic field lines. And we want to find the EMF in this coil here, which we can picture it like, say this is, yeah, we wrap this wire around the toroid. So this coil here, whatever we call it, it would look something like this. And so we can see that there's a magnetic flux through this coil. And if we had just a constant current, that would be a constant magnetic flux. Not much would really be happening here, but the current is changing. And so first, let's look at the magnetic flux in this coil. Let's call this coil, here, let's do this. Let's call this coil C. We'll call this T for torque. So we want to find the EMF in that coil C. So first we need the flux. So to start with, let's apply Ampere's law. Remember Ampere's law that the integral of B dot ds around some closed path is equal to mu naught I, where I is the total current passing. So if we have a closed path, that encloses an area. And so I is the current. So we have, we have a surface now defined by our closed path. So to do this integral, we have to have a closed path, and that gives us this area. And so we can talk about the current, whatever current passes through that surface. That's I. So let's apply Ampere's law to this loop here. So we'll draw a loop at a given radius r. So at a given radius r, now we're going to do this magical thing that happens where the integral of B dot ds is going to be the integral of B ds. Because we have the magnetic field lines are circular, and we have a circular Amperian loop, and so B dot ds is going to be B ds. We don't have to worry about the direction, and also at any given radius, the magnetic field is going to be constant as you go around the loop because we're always the same distance, and just from symmetry, we have to have B times the integral ds. And remember, ds, that's like an arc length, like an element of arc length. So what we're doing is we're taking this loop, breaking it up into pieces and adding up the length of each piece. And so, of course, what we get then is the circumference of the circle. So what we have here is B times 2 pi r. That's equal to mu naught times I, where I is the current that's passing through this surface. And it passes through 500 times. Oh, I wrote n equals 500 n. I don't know why. N is just 500. It's a number. So yeah, we have one wire carrying a current, but it's crossing a total of 500 times. So the magnetic field at a given radius so it does depend on the radius. And the current is also changing with time, but let's leave that alone for a moment. So if we look at this cross section, we have kind of a stronger magnetic field here, but it gets weaker as we go to the outer edge of the toroid, because as R increases, the magnetic field decreases. So we can't just calculate the flux by doing magnetic field times the area. We have the area, that's just A times B, that's trivial. But usually when we calculate magnetic flux, it works out that it's magnetic field times area. It's not going to be quite so simple in this case. So let's draw another picture. Let's say this is the cross section of the toroid. And so let's look at a given, so like here's the center of the toroid. So let's look at a given radius. The magnetic field from top to bottom is going to be the same. So let's calculate, let's call it d phi. Let's say this has we're looking at a thin strip that has a width of dx, and then the height of this strip is a. So as long as that's a thin strip, we can consider the magnetic fields here constant. So the flux here would just be the magnetic field times the area, which is A dx. And if we plug in the magnetic field, we have mu naught Ni dx. Oh wait, forgot A. I'll just put it in there. Okay, so B is mu naught Ni over 2 pi r. So that's B, and then we have times A dx. And then to find the total flux, we would just integrate that from the inner radius to the outer radius. Now, in doing this integral, we can take out all of our constants. Now, I is definitely not constant, but we can still take it out of the integral because we're integrating over space. I depends on time, but at any given time, I is constant. So we can take everything out here, including I. So the total flux I'm going to call this R instead of X. No reason to have two letters when basically both saying the same thing. So the constants are mu naught Ni A over 2 pi, but then we have dr over R. And we're integrating from the inner radius, which is R, to the outer radius, which is R plus B. Now, thankfully, this is a relatively simple integral. The integral of dx over x is the natural logarithm of x. We don't care about the absolute value because we're dealing with positive values. And yeah, we're going to get a positive. We don't have to worry about that. I'm going to do this off to the side, though, just because we're kind of running out of room. So let's do like just a general integral. The integral from, say, A to B of natural log x, or sorry, 1 over x dx. So we know that the natural log of 1 over x dx is a natural log of x. So we have the natural log of x evaluated between A and B. Now, I'm not going to have enough room to write this, but what we have here is ln B minus ln A, which is ln B over A. And again, because it's positive, we don't have to worry about the absolute value. Okay, so here we have, I think I'm going to have to erase some stuff. Yeah, I'm going to definitely have to erase something and just write the result up here. So, yeah, we just have mu naught Ni over 2 pi times the natural log of R plus B over R. So I'm going to erase the work getting to there. But before I do that, are there any questions on getting this result? Okay, so let's write this down. So the flux is going to be mu naught Nia divided by 2 pi times the natural log of R plus B divided by R. Basically, it's the outer radius divided by the inner radius. So I'm going to leave this picture up that shows how we did the integral. We consider this rectangle here, a very thin rectangle. So the flux, I'll write this part here. the flux here is just B or d phi, the flux element, due to that little rectangle at a radius r. That would just be the magnetic field at that radius times the area, which is A dr, just the height times the width. And so again, this is constant from top to bottom, so we don't have to integrate vertically, just horizontally. And we use Ampere's law to find Vr, and then we integrated from the inner radius to the outer radius to get the total flux. And we could also, this will depend on time. Let's see if we can write this overall. All right, now let's put this I max. So the flux as a function of time, all we did is plug in our current here. So we have mu naught n, let's ignore the I for a minute, mu naught n A over 2 pi times this logarithm, which is just a constant because R and B are given. So this is just a number, basically. And then the current is I max times sine omega t. So basically, the flux is just a constant times sine omega t. So are there any questions on that? Oh, actually, there's one more thing we have to do. Let's call this phi 1. Because we're looking at the flux through this coil. So this would be the flux through a single loop of that coil. So if we want to look at the flux through the entire coil, we'd have to multiply by the number of loops in the coil, which is n prime. So now we have the total flux through the coil here. Now let's see what the question is actually asking us. Determine the induced EMF in the coil as a function of time. So we've done the hard part. Now we want to find, we can apply Faraday's law. They're asking for the EMF. So what we want to do is take the derivative of this as a function of time. And that is actually trivial because remember, all of this is a constant. So actually, just because I don't think we'll have room to do this, let's define phi max equal to mu naught n prime a I max over 2 pi and then times the natural logarithm So let's just define phi max equal to all of that. And then we can say that the flux through the coil is phi max times sine omega t. And now you can see that taking the derivative is going to be trivial. This is a constant, so just the derivative of sine omega t is omega times cosine omega t. So derivative of sine is cosine, but we pull out an omega. So the EMF, we're going to have minus, and then we have our constant times omega, and then times cosine omega t. So that would be the EMF in our coil. All right, so any questions on that? Now, we can do one more thing. Let's define the maximum EMF to be phi max times omega, because that is the maximum EMF, because just like sine, the maximum value of cosine is going to be 1. Or in this case, there will be a time when cosine is -1. Cancel out that minus sign. And so when that happens, that's the maximum EMF in the coil, which is phi max times omega. So what I'm going to do, well, this is being recorded, hopefully. There were some issues with recordings, but I'll try to check this tonight, and once they process it and download it before they delete it. So I always like to do like a numerical calculation. And again, the hardest part is just going to be getting the units to work out. We should get volts out of this. So let's find the maximum EMF that we can get. So I'm going to have to erase just about everything. And maybe we'll do this calculation in pieces. So I don't want to erase this, but it's being recorded. You can always back up if there's something you need. So we need phi max and then just multiply it by omega. So to start with, let's look at the maximum EMF. So that would be phi max times omega. We'd have mu naught n prime a I max. Let's throw the omega on here. Now we can actually simplify this. Omega divided by 2 pi is the frequency. So let's do this. Now that we have omega over 2 pi, we'll just replace that with frequency. So we have mu naught n prime a. Let's throw our frequency on there times I max times the natural log r plus b over b. So that's the maximum EMF that we can get. And we have all our numbers over here. I'd kind of like to erase those as well, because I have a feeling this is going to take a lot of space. So maybe we can erase the toroid. We've seen it. Clear up as much room as we can. Let's do one thing. Let's just let's see. Let's calculate this in pieces. So to start with, let's calculate n times n prime times this natural logarithm of r plus b over b. And the reason I want to like isolate these variables is if we multiply, this is just a number. Remember, r plus b, we're going to have centimeters over centimeters. That's dimensionless. These are just numbers. So let's do that. So we have 500 times 20. That's 10,000. So let's just do this natural log first. We have the natural log. So r plus b is 7 centimeters. And then divided by 3 centimeters. So that's 0.847. And so then if we multiply by 500 times 2 is 1,000, and times 10, that's 10,000. So this should be 8,423. Sorry, 73. Let's give that a name. Let's call that C. Just a little shorter than writing it all over the place. So now let's find the maximum EMF. Now maybe we'll just write down this number. 8,473. Then mu naught, which is 1.26 times 10 to the minus 6. Tesla meters per amps. So we've got mu naught. We already took care of n prime and this natural logarithm. We've got that. Now A is, let's say, 2 meters over 100. We've got A. F is 60 hertz. That would be 60 cycles per second. And Imax is 50 amps. So we've got to get this into volts. So let's see how we can do that. We have Tesla meter squared per second. There's something in the equation sheet, which I do not have with me, unfortunately. One of those unit conversion factors. Let me try and work this out on the side, just to take up as little room as possible. So what we have is Tesla meter squared per second. So the challenge is going to be getting volts out of this. A Newton times a second is a Coulomb meter times a Tesla. Oh, maybe it won't be as bad as I thought. And remember, a joule is a Coulomb times a volt. So we can say a Newton times a meter is a Coulomb times a volt. So Coulomb, volt, Newton, and meters. And yeah, I think this will actually work out. So let's draw these two conversion factors. Okay. So let's look at the units here. We have Tesla times meters times amps, Newton, seconds, coulombs, and volts. Again, let's double check. Tesla, meter, amps, Newton, second, coulomb, volts. On the bottom, we have amps, seconds, coulomb, meters, Tesla, and Newton, meters, and we actually do get volts. So at EMF, the maximum EMF in volts, we have 8,473 times 1.26 times, I'll shorten this a little bit, 2 times 60, say 1, or no, let's make it even simpler. Here's 60, 50 and 2 is 100. So we have 6,000. And that covers all the numbers on top. And then on bottom, we have 10 to the 8th power. So let's see. This might not be too unreasonable just to leave it how it is. I think it'll be less than 1. So let's see. We have 8473 times 1.26 times 6,000. Being lazy and just letting the calculator do everything. Yeah, this is 0.64 volts. So that'd be the maximum EMF on that coil that we wrapped around the toroid. So kind of a fun problem to do because it involved, like, that was, I think, the first time so far in this class where we had to calculate a flux that wasn't just the magnetic field times the area. So you always want to, be careful when you're calculating flux. It's not always B times A. So you always have to look out for that. And that's one problem I've noticed that in this class is just recognizing when you have to use calculus or not. So hopefully this problem made sense. Now, are there, it was recorded, so you can always look back on it, but are there any questions on this application of Faraday's law? Okay, now I'm actually going to stop recording and then start again. So I'm going to have two videos. So let me stop it first.